All right, so let's keep practicing and seeing if other things are binomial as well. So we have a loaded die that tosses 5s 80% of the time. We're going to toss the die 4 times and record the number of 5s, right? And we have to explain whether or not this is binomial or not. All right. And the answer to that is yes, it is binomial. Now let's give you each of the pieces. So we start with a fixed number of trials. Well, that's definitely yes, because it's performed 4 times, right? So n equals 4. All right, so we have our n value, and matter of fact, I'm going to underline it right now, so that way it's done. Okay, now what about our trials independent? Okay, well, dice don't have any memory. We learned about them back in chapter 5. Dice are very much independent. That's one of the reasons they're involved with classical probabilities so much. So absolutely, the die, it's one die, but you're tossing it multiple times. It has no memory of its last toss. That makes it independent, right? Now, are there 2 disjoint outcomes? Yes, indeed, there are. There's success, which is rolling a 5, because we've determined that 5s are what constitutes success for us. And then all the other things are not 5s, and therefore they're not success. They're failure. And so I just wrote that up. So success is rolling a 5. Failure is not rolling a 5. Yes, you do have to write that out. And then you have to write out what your x is. X is your random variable. So it's the number of 5s, the number of successes in 4 tosses. So that means you could have as low as 0 5s all the way up to 4 5s. Now, is the probability of success the same for every trial? Sure. It's not even because it's a loaded die, but that doesn't mean that it's not the same, right? This loaded die is set up to be 80%. So the probability of success is 80%. And that means the probability of failure is 1 minus that. They're complements of each other. So this one is definitely binomial. And you can see how many points this is going to be worth on a test. A lot of them, right? Because it's going to be, you're going to get points for every part, everything that you're writing. You're going to have to find all the things that are underlined. So it's usually worth about 7 or 8 points on an exam. All right, now what if you have a loaded die that tosses 5s 80% of the time, and you're going to toss that die and record the number of rolls it takes to obtain a 3. So you're going to keep rolling and rolling and rolling and rolling until you get a 3. Well, that is not binomial. You're losing number 1 right off the bat because you don't have a fixed number of trials. You don't know how many times you're going to have to roll this to get a 3. So little n, your sample size, is not fixed. All right. What about the Agency for Healthcare Research and Quality reported that 53% of the people who had a coronary bypass surgery in 2008 were over the age of 65. 15 random coronary bypass patients are sampled, and the number who are over 65 is recorded. Okay, well, just going to give you the idea here. This one is also binomial. Let's see if I can fit that in there. Nope. All right, so now why is it binomial? Well, we're going to have to show it. It's going to answer all of our items. So first thing is that it's performed a fixed number of trials, right, for sure, because you have 15 patients, right? This number 15 gets you your fixed number of trials. So there's n right there. Done. Then we need to have the trials be independent, but of course they must be because patients are random, right? Since the patients are random, you can assume that they don't really have any bearing on each other. So it's a little bit fuzzier than a die, right? The dice and the NBA players, it was kind of obvious that they must be independent. But here, this word random is causing it to be what you think it is. It's causing it to be independent because if I'm a patient that has a coronary bypass, I really have no bearing on another patient that has a coronary bypass that is a random patient, right? As long as they're not relatives and stuff, we're random, then we're unbiased and independent. Okay, now are there 2 disjoint outcomes? Sure, indeed, there are 2 disjoint outcomes. And what is that? Well, it's a little bit weird to see, but we're looking for the number who are over 65. See that? So the number who are over 65, that's counting as success for us. Let me give him green. So success is the number over 65. And that means that success is over 65, then failure is 65 or less, right? And then X would be, because we have to convert that qualitative idea of success and failure into a number. So it's the number of coronary bypass patients who are over 65 out of the 15 patients total. And I was not going to write all these numbers out. So this is when you put in an ellipsis, dot, dot, dot. If you put in the dot, 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 it's implied that it just keeps going and going and going like that. There we go. All right, so now what about the last one, which is the probability of success the same for every trial? Well, sure, absolutely it's the same because, again, it says that it's 53% of all the people who had the coronary bypass were over 65. That's not really going to get affected by anything, right? So it's going to be consistent because it's for the whole of the country, if you will. So that means the probability of success is P, which is 0.53, and then the probability of failure is Q, which is 1 minus 0.53, which is 0.47. Now I just want to highlight some things here. So the 15, that yellow part, that's where I know that this is 15. So I can give that a yellow highlight just to match. The random part is giving us this right here. So that's how we know that they're independent, as opposed to if they took 15 people from the same family or something. That would be bad. Well, it wouldn't necessarily be bad, but it would not be binomial, that's for sure. And then the number who are over 65, that's determining what it makes success for us. So success is over 65, right? And that also helps us determine what our X value is. And then the probability of success is pink or magenta, whatever color that is, right? That's where that's coming from. So one little phrase with 3 lines, and it's giving us a whole bunch of information. And this is definitely a binomial experiment. Now for the last one, we have a jar containing 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. Uh-oh, oops. That's a problem. I'm going to flag that right off the bat. Without replacement is always kind of problematic. And the random variable represents the number of red marbles chosen. All right, that is not binomial. And the problem is you're doing it without replacement. Right? So you randomly select 3 marbles from the jar. So n is 3, right? You've got your fixed number of trials, but you're going to be losing both number 2 and number 4. And that usually happens together. I mean, if you break in rule number 2, if they're not independent, then you're usually going to be losing your probability of success as well, because the probability of success is consistent because they're independent. Okay? So once we have it without replacement, because the marbles are sampled, sampled without replacement. That breaks rule number 2, and the probability of success will keep changing. So in general, experiments done without replacement are not binomial because of what we're seeing above. It violates independence, you lose independence, and you lose your probability being consistent because you're losing independence. Now that said, what if this was, instead of a jar containing this many marbles, what if you were at the factory and it was 100,000 marbles? Just a huge vat of marbles, something you go swimming around in. Then if you just take 3 out, are you really violating that independence? Well, yes, but it's so minor. It's such a small amount that we'll basically fudge it and say it's good enough. And we'll talk about that more in chapter 9 and 10. So we'll talk about that more then.